All right, welcome everybody. Today we are going to talk about lesson number 95. This is our second to last video for the year, the start of our final section 12.4, limits at infinity, which we're going to talk about today, and then limits of sequences, which we're going to talk about tomorrow. You'll see homework 95 there. Again, it might look like a lot of problems, but I promise it isn't, especially since I'm going to start the lesson by showing you kind of the longer process of how you would evaluate some of these limits, and then I'm going to show you the shortcut, and you are, of course, welcome to use the shortcut tonight for the homework. All right, what we're going to talk about is we're going to talk about limits at infinity. And it turns out that when you're talking about limits at infinity, they have a direct correlation to those horizontal asymptotes, the things that we talked about back in chapter 2, specifically section 2.6, which is, of course, about rational functions. Reminder of what it actually means to be a rational function. It means that you have polynomials in the numerator and denominator, which essentially means you have x's in the top and x's in the bottom. As a little bit of a reminder here, remember one of the biggest things you're going to talk about next year in calculus is how to find and use tangent lines. That's really what we've been talking about for the past couple of lessons. The second big thing you're going to talk about in calculus is how to find the area of a region. Now, we're not really going to get into that at all this year, but it is something that's important for next year. But again, the problem in question here is the rational function x plus 1 over 2x, and we're going to talk about where the graph would be approaching as x goes to both positive infinity and negative infinity. If you look over here on the right-hand side, this is the graph of that rational function. So again, let's review about how we would create that if we didn't have our graphing calculators. Again, if you go back to your chapter 2.6 notes, you would start by finding the x-intercept, which would mean you would set the numerator equal to 0, which would be -1. You would find the y-intercept by putting a 0 in for all the x's, which would be undefined, which is none. A vertical asymptote would be found by setting the denominator equal to 0, which would be at x equals 0, the vertical line. And then finally, the horizontal asymptote. If you were to look for the horizontal asymptote, you would, of course, compare the degrees. Because they are both linear to the first power, you would look at the coefficients, which would be 1 over 2, which would tell you that there is a horizontal asymptote at 1/2, which is, of course, indicated in the graph by that dotted pink line. So when they're asking you for the limit, as x goes to negative infinity, what they're saying is as the x values get smaller and smaller and smaller and smaller, where are the y values approaching? Well, clearly that's the horizontal asymptote of 1/2. That should be relatively obvious because that's kind of the whole point of a horizontal asymptote. Similarly, on the right-hand side, as the x values get larger and larger and larger, where are the y values approaching? Well, they are also approaching 1/2, again, because of the fact that that is the horizontal asymptote. This is just kind of formalizing that process a little bit and kind of telling you how you would say it in words. We haven't seen any problems so far where these values were positive and negative infinity. Up to now, they've always been a number, but again, it matters not. So this is just telling you that you can find those limits. Limit 1 would be as you go to negative infinity, and limit 2 would be as you go to positive infinity, and those just stand for constants. The first statement, you would say the limit of f of x as x approaches negative infinity is 1/2. And then the second would say the limit of f of x as x approaches infinity is 1/2, or again, whatever particular value it was in your problem. Another very important limit rule, so make sure you write this down. If r is a positive real number, then the limit as you go to both positive and negative infinity of 1 over x to the r is always going to be equal to 0. So again, consider what they mean when they're talking about r being a positive real number. Okay, so that means that if you had 1 over x to the first, 1 over x squared, 1 over x cubed, and that could also be something like 1 over x to the 3/2 or something like that. If you are trying to talk about the limit, which means as x gets larger and larger and larger, if the numerator is 1, and honestly, if the numerator were any constant, 5, 10, 20, anything, because of the fact that the denominators continue to get larger and larger and larger and larger, while the numerator remains constant, you can clearly say that if you divide a small constant by an ever increasingly large number, you're going to result in a very, very small number, which is essentially 0. And that's why the limits are defined as such. So showing you a little bit of an application of that, let's say I wanted to find the limit as x goes to infinity of 4 minus 3 over x squared. If you think back to all the limit rules we've done so far, you're allowed to break this subtraction up into two separate limits. Then if you wanted to take the constant 3 from the numerator and factor it out to turn it into a 1, just so that it would exactly mirror the rule on the previous slide. But again, spoiler alert, this works for any constant. The limit as x goes to infinity for 1 over x squared. Again, the top is going to remain constant, where the bottom is going to get infinitely large. If you divide a constant by a big number, you're going to get a small number, which is essentially 0. And whether you multiply 0 by 3, you're still going to get 0. The limit of any constant will always be that constant, which means your limit to this entire problem is simply 4. This shows you that graph of 4 minus 3 over x squared. And then notice here, this is asking you for the limit as x goes to negative infinity. You would have a very similar set of steps, and you would still get a limit of 4 for the exact same reason. For this term right here, because the bottom is getting bigger and bigger and bigger, whilst the top stays the same, this entire term goes to 0, and that's how you're going to get a limit of 4. So this is showing you, graphically speaking, how that would occur. And then there are some calculus limit steps to kind of verify that this is true. And that would involve dividing every term in the numerator and the denominator by the highest power term of the denominator. We're going to see that in a minute. But for now, let's just do an easy example. So here in example 2, find the limit as x goes to negative infinity of 7 minus 1 over x squared. So again, you can, using the properties of limits, break this up into two separate ones. Even though you're going to negative infinity, because of the fact that you're squaring it, it's getting infinitely larger and larger and larger. So if you're dividing 1 by a large number, that limit, based on the rule from a couple slides ago, is going to go to 0. The limit as you approach anything of a constant is always going to be that constant, which means the final answer to this problem is simply 7. Now, you're probably wondering, if I know that, do I have to show this work? The truth is, for me, no. The whole point of this lesson is you're going to kind of understand the shortcut. For next year, I don't know, because some of the problems on the AP test might require you to show your work and explain it. So make sure that you're not blowing it off altogether. This is kind of showing you that technique of dividing both the numerator and the denominator by the highest power term in the denominator. And again, this is how you would prove it, show it, explain it. So here in example 3 is the rational function in question, negative 2x plus 3 over 3x squared plus 1. Again, the technique here will always be to divide everything in the top and bottom by the highest power term in the denominator, which of course is x squared. So from this original problem to the next step, notice that I'm dividing each of these 4 terms all by x squared, and then I simplify them. That results in this right here. For these 4 values, in any of the scenarios where the degree is larger in the denominator, those limits are going to go to 0. 3 divided by a big number, 0. 1 divided by a really big number, 0. Negative 2 divided by our big number, whether it's going to x to the first or x squared, the denominator is still getting infinitely larger and larger and larger. So that's why you're getting 0, 0, and I guess negative 0, although it doesn't matter. The only term that actually has a limit is this 3 in the bottom here, but because the numerator turns out to be 0, 0 divided by anything would of course give you a limit of 0. Showing you that technique in a similar problem, notice here that you have negative 2x squared in the numerator, and you also have a 3x squared in the denominator. Again, the strategy is always to divide by the largest degree term in the denominator, which is still x squared. So if I divide each of these 4 values by x squared and simplify, I get this right here. 3 over x squared, that's going to go to 0. 1 over x squared, that's going to go to 0. The limit of negative 2 and the limit of 3 are simply themselves. And if you go ahead and find that ratio, the limit of the entire thing would go to negative 2/3. Finally, let's say you had negative 2x cubed and 3x squared. Again, you're going to divide everything by the largest value in the denominator, which is x squared. If you go ahead and simplify, you get the following. Bigger in the denominator, these are going to 0. And then notice you're left with negative 2x over 3. The denominator is going to remain a 3, where the numerator, if the x gets bigger and bigger and bigger and bigger, well, then the top is just getting bigger and bigger and bigger. And if it just continues getting bigger, then you're not going anywhere, which means that the limit does not exist. Now, if you're asking yourself, why is this familiar? Don't I kind of already know this? Well, yes, you do. In summary, limits at infinity follow the same rules as horizontal asymptotes of rational functions. So this entire screen right here simply summarizes those rules in words. So read through them as closely or as not closely as you need, but it basically just summarizes what's going on. The fact that you are looking for, again, the highest degree power of the polynomial, that's what we call the most influential term. So again, this is just the word summary of what's going on in these rules. Here are the rules and plainly stated, which again are the same rules that we learned back in section 2.6. And they're the rules for how you would find horizontal asymptotes of a rational expression. You would compare the degree of the numerator, which in this case they're calling n, to the degree of the denominator, the largest one, which would in this case they're calling m. If the degree of the numerator is less than the degree of the denominator, then they're going to say that the limit or the horizontal asymptote is going to be at 0. Again, that means it's bigger on the bottom. So the bottom gets bigger and bigger and bigger, where the top stays the same. That's 0. If the degrees are the same, then you're going to find the horizontal asymptote by doing the coefficients, a over b. And if the degree is larger on the top compared to the bottom, that means it's not heading towards any particular number, which means there is no horizontal asymptote. And hopefully you remember back from your rational function days, that means there's an oblique asymptote. So again, you probably or hopefully remember these rules. If not, review them. And then this is the book. The way it's the same exact rules as the previous slide, but they give it in terms of limit notation. And honestly, I think it's in a way that's just harder to understand. So I wanted to show you, again, 3 different versions. The words explaining it, the old rules for horizontal asymptotes, and then these are the specific limit rules, but the truth is they're the same. Here are 3 examples where, again, the direction would be to find the limit at infinity. So again, on your homework, do you have to show me all that work of dividing through by the x squareds and then showing what happened? You do not. Will you have to next year? Possibly. So again, don't blow off the technique altogether, but using the shortcut is kind of the goal. So here in the first one, if you're going to talk about finding the limit at infinity, you're going to look at the largest degree on the top and the largest degree on the bottom. So you're trying to find the limit as x goes to infinity of that function, which we'll just call f of x for short. Because of the fact that the x squared in the denominator is larger degree than x to the first in the numerator, the bottom is always increasing faster and faster and faster. So you have a smaller number divided by a larger number on the bottom. That means that the limit at infinity is 0. In this second example, you're trying to find, again, the limit as x goes to infinity of that function f of x. When you compare these degrees, you can see that because of the fact that they are squared and squared, they have the same power, which means they would essentially cancel, which means the limit is the ratio of those powers, which would be -1 from the numerator and 5 in the denominator. Finally, here in the last one, you would compare again the largest degree to the largest degree. Because of the fact that in the numerator, you have a higher degree, that means that the numerator gets larger and larger and larger. If it just gets larger and larger and doesn't go anywhere, then that is what we would call a do not exist. So when it comes to the homework problems, which the majority of them are like this, I'm fine if you kind of just use the shortcut, keeping in mind that at some point next year, you might not be able to. Last but not least, one last topic for today is something called finding the average cost. And we actually did plenty of these back in section 2.6. Again, if you go back through your notes, there were problems about gym memberships and fruit stands, and that one from the quiz about the saltwater solution. But here, why is it even in this chapter? Well, it has to do with rational functions. So suppose you're manufacturing greeting cards and they cost 50 cents each to produce, but you have to invest $5,000 in the machine and the paper and the ink and all that kind of stuff. If you are trying to figure out the total cost of making your cards, it would be 0.5x plus 5,000, essentially y equals mx plus b, the y-intercept being 5,000, and then 50 cents per card. Whenever you see something that's asking you for the average cost, the notation for an average is the variable with a little line on top. And then if you think about how you take an average, you divide by the total number of things. And if you don't know the total number of things, then you're going to call that x. So this is an example here of an average cost function. And because it looks like a rational function, that's why it's in this chapter. So what's the average cost when x equals 1,000? Well, plug 1,000 in for each x, simplify. So if you were only going to make 1,000 cards, it would cost you approximately $5.50 per card, which is a lot because you'd have to sell them for more in order to make a profit. What's the average cost for 10,000? Well, everywhere there's an x, put a 10,000. What's the average cost for 100,000? Well, everywhere there's an x, put 100,000. As you can see, the average cost per card is going down significantly as you make more and more cards. Why is that? Well, it's because of this $5,000. You have to pay that $5,000 no matter what. So either you're dividing that $5,000 by something like 10,000, or you're dividing it by something by 100,000. So the more cards you make, the more evenly that $5,000 gets distributed, which lowers your average cost. The last question in D said, what was the limit as x approaches infinity, which basically means what's the cheapest you can produce a card for? Well, again, this is a rational function, so compare the degrees. Because they're the same, you would do the coefficients, which would give you a limit of infinity of 50 cents. And again, hopefully that makes sense because at a certain point, if you're making 10 million cards, this $5,000 divided by 10 million cards is so arbitrary, close to zero, where no matter what, you have to pay that 50 cents per card.